Okay, so we are happy to have with us here today Matthew Jenssen, who will talk about some recent work on homomorphisms from the torus. And please, you can get started. So if you are, yes.
Okay, great. Yeah, thanks so much for the invitation to speak here. It's really cool to be able to connect with people so far away. And thanks for accommodating the shift in time. As you can see, it's nighttime here in the UK. Okay, so everything I'm going to talk about today is joint work with Peter Keevash at Oxford. And let me start by introducing a notion at the intersection of combinatorics and statistical physics, which is where most of the talk will take place at this interface. So the notion I want to introduce is that of a graph homomorphism. And by the way, please ask any questions if I'm going too fast or too slow or haven't defined something. Feel free to interject at any point. Okay, so suppose I have two graphs G and H. A homomorphism from the graph G to the graph H is basically a map that preserves edges. So if U and V are adjacent in G, then I want that image to both be adjacent in H. And I'm going to let hom G comma H denote the set of all homomorphisms from G to H. So homomorphisms provide a unifying framework for a number of important graph theory notions. So let me give you two examples. If I fix H to be a clique, so K sub Q is a clique on Q vertices, so Q vertices where every pair is connected by an edge, then what am I asking for? I'm asking for that every edge gets matched to an edge of the clique. That just means that every two vertices joined by an edge need to get mapped to two distinct vertices in my clique. Or in other words, I'm looking at a proper Q coloring of G. So I'm going to the vertices of G, assigning some color, and I want this color to be proper. If I take H now instead to be this funny graph here with a loop at it, if you squint at it for a second, you notice that the homomorphism into this graph is actually nothing more than an independent set in G. So an independent set is another important notion in graph theory, which is just a collection of vertices with no edges between them. Okay, but for the statistical physicists, homomorphisms come up naturally in the study of spin models. And let me give you some examples. So you can put some really nice probability distributions on this set hom GH. For example, if I weight the vertices of H, so here let me assign every vertex of H some positive weight, then I can decide to select a homomorphism from G to H with probability proportional to the product of all these weights. And I'm going to give a couple of examples in a second. So this is called a spin model. And the statistical physicists might complain at this point and say this is a rather restricted class of spin models. For example, I'm demanding hard constraints here, and this doesn't include important models like the Ising model or the Potts model. But this already includes some of my favorite probability distributions, and I'll mention this more general framework. I'll return to that at the end. So here are some examples. Again, let me fix H to be the clique on Q vertices. So I'm looking at proper colorings of my graph G. And let me be boring and just assign everything the same weight. Then what am I doing? I'm picking a coloring proportional, with probability proportional to, well, all of these are just one, proportional to one. So the uniform measure on all Q colorings of G. If I look at the second example, with this looped graph again, and weight one vertex with the weight 1 and the other with some positive parameter x, what I get is known as the hardcore measure in G. And what's the hardcore measure doing? It's selecting some independent set I with probability proportional to x to the size of I. So for small x, I'm biasing towards small independent sets, and for large x, I'm biasing towards large independent sets. So for the most part of this talk, I'm going to be concentrating on this first example for simplicity, but I'll come back and mention the general case at various points. And already this first case, now just a uniform Q coloring of graph, is going to contain most of the ideas, and you can get a flavor of the results just by looking at this case. Okay, so these kinds of spin models are traditionally studied on the integer lattice Zn. So here I've drawn a picture of Z2. So just strings of length n with integers, and I join them by an edge if and only if they differ in exactly one coordinate by 1. And this provides a nice setting where the phenomenon of phase coexistence and phase transition can be rigorously studied. So I'm not going to go into a sort of formal definition of what these things mean, but let me at least mention two landmark results in this field. So the first one I want to mention is due to Galvin and Kahn, and then later also Pellet and Samoti, where they study the hardcore model on Zn. And really, I want you to be thinking of it in n large, even though I've drawn Z2 here. What they show is that as soon as this parameter x, remember this was the degree to which we were biasing towards small or large independent sets. So again, small x, I'm going to be typically selecting a small independent set, and as I crank up x, this independent set should become denser and denser. If I take some large box in Zn, then what they show is that a typical sample from the hardcore model, as long as x is bigger than roughly n to the minus 1/3, a typical sample exhibits long-range correlations. So this is a very informal statement of what they prove, but let me give you a flavor. So here's a picture of maybe some independent set in Z2. So these gray dots I want you to think of as vertices in my independent set, and white dots as vertices out of my independent set. And by long-range correlations, I want you to sort of think as they start to correlate with one of two sublattices, the even and the odd sublattice. So you could look at all the odd vertices or all the even vertices. And in this picture here, most of my independent set has started to concentrate on one sublattice. Except, well, in this picture, except one deviant vertex, which is sort of going against the grain. And what I want you just to notice here is that there's a cost to going against the grain, just to start to build some intuition. So if I put a vertex here, I have to unoccupy. I can't have any vertices in my independent set in any of my neighbors. So by long-range correlation here, I just mean to start to crystallize on one of these two sublattices. And this is supposed to be a very simple model of a gas freezing. So for example, an independent set, you can think of the vertices of the independent sets as atoms. And the fact that they're independent is some sort of spatial condition that they don't overlap. And so at low density, there are no long-range correlations. Our independent set doesn't have to exhibit any kind of structure. But as I crank up the density, and here we see the density doesn't even have to be that large, it can even go to 0 with n. But as we crank up the density, we start to see long-range order. And we can kind of think of this as this very toy model of a gas going from disorder to order, freezing. Okay, so this is a vague introduction to those results. And the other result I wanted to mention was by Pellet and Spinker.
By the way, sorry, but is the n to the minus 1/3 optimal there?
Great question.
No?
Yes, I should have mentioned, so n to the minus 1/4 was done by Galvin and Kahn, and then n to the minus 1/3 later by Pellet and Samoti. Yeah, it's conjectured that this is not optimal. Something around 1/n should be the truth.
Oh, okay.
Modulo some logarithmic factors. Yeah, so
you.
this is all that's known. But yeah, I don't think anyone believes that this is optimal. Great. So Pellet and Spinker do the same thing, but now with this other example we've been looking at, which is Q coloring. So suppose I take a large box in Zn and take a uniform Q coloring. So here I've used 4 colors. What does it mean to have large-scale structure in this case? Well, here we might expect on one sublattice to see 2 colors, and on the other sublattice, the other 2 colors. So I've evenly split the four colors in the odd sublattice and the even sublattice. And that's the kind of large scale structure that we're seeing here. And this is precisely, well, not precisely, but this is roughly what they show, that a typical Q coloring starts to look like one of these phases where I put half the colors on one sublattice, half the colors on the other sublattice. These long-range correlation statements are enough to show that, if you like, that there are multiple infinite volume Gibbs measures you can put on the lattice Zn for sampling Q colorings. Okay, but again, in my picture here, not every vertex, of course, you're not going to expect every single vertex to follow this pattern. Here we see this red vertex is going against the grain. And again, I just want you to notice that this comes at some kind of entropy cost. What do I mean by that? So before, these blue vertices had a free choice between being blue or red, and now they're forced to be blue. So before I had two choices, and now I have one choice. And similarly, these green vertices are going against the grain, and all of their neighbors, their choices are restricted. So there's somehow this entropy cost of going against the grain is what's causing this large scale structure. Okay, but what I wanted to talk about today is how to study these same problems, but in a more combinatorial setting, and I'll explain what I mean by that in a second. But we're going to be using a lot of tools from classical statistical mechanics that are used for the lattice in the combinatorial setting to prove some very strong statements there and prove some conjectures. And then at the end, I'll try and say a few words about bringing it back to this classical setting, how I hope that the methods I discussed today can be used again in this traditional setting. So now might be a good time to ask if there are any questions. Okay, great. So the setting I'm going to be looking at is the discrete torus. So this is the lattice, but now I've put these periodic boundary conditions on. So formally, the discrete torus is the graph on vertex set 0 up to n-1 to the n, so strings of length n, and my entries are 0 up to n-1. And I'm going to join two vertices if they differ in exactly one coordinate. And in that one coordinate, they differ by 1 modulo m. So this is the discrete version of the torus. And crucially here, I'm going to be thinking about m fixed and n large. So this is what I mean. This is what's making this regime why I'm saying this regime is combinatorial. So I'm also going to be assuming that m is even, so that this torus is bipartite, like the integer lattice is. And I'm going to call the two parts of the bipartition odd and even, O and E. So again, the odd sublattice and the even sublattice, all strings whose sum is even and all strings whose sum is odd. And if we fix m equals 2, we get this familiar combinatorial graph called the n-dimensional discrete hypercube, which I'll use the more familiar notation Q sub n. Okay, great. So what we show, and let me now first state our theorem in vague terms, and then hopefully these terms will crystallize throughout the talk. What we show is a sort of very strong, if you like, phase coexistence type results for these measures on the torus. So what we show is that this measure mu h lambda on the torus can be very closely approximated by another measure mu hat, which we define constructively as a random perturbation of some dominant phase. And here I want you to be thinking of dominant phase as the kind of the dominant phase as I showed you in the Peled-Spinker and Galvin-Kahn theorems. We will elucidate all of these terms in the coming slides. And what's important here is that we can really understand in great detail what this random perturbation is. We'll really be able to get a very strong handle on the distribution of these random perturbations. And therefore, we'll be able to get a very strong understanding of our original measure. So that's our theorem in vague terms. And now let me just zoom in on one specific example, this Q coloring model. So again, now I'm just looking at a uniform Q coloring on the torus. And instead of mu at h lambda, let me just write mu sub q for the uniform measure in Q colorings. So if you like, the question now is, what does a typical Q coloring of the discrete torus look like? And let's try and understand that as well as we can. Okay, so in order to discuss these things a bit more formally, I'm going to have to introduce a little dictionary of terms so we can discuss these things. Hopefully you have access to the slides as well. I think Omer sent a link so that you can flick back and forth between slides if something becomes unclear.
So there is a link on the chat.
There's a link on the chat, great, yeah. Or just ask me. But yeah, it might be useful to be able to go back a few slides. Okay, so what do we mean here by a pattern? So a pattern, I'm going to say, is that a pair A, B, these are now both subsets of my color set, and they're going to be disjoint. So for example, if Q equals 6, one pattern might be 2, 5, comma, 1, 3, 4, 6. And what this means is I'm going to be coloring one side of my sublattice with set colors from set A and the other side with colors of set B. And notice that any assignment of colors 2, 5 here on the left and 1, 3, 4, 6 on the right is a legitimate coloring, a legitimate 6 coloring, because we only have edges going across here. This is a bipartite graph. Okay, and I'll call a pattern dominant if I've split the colors up as equally as possible. So the pattern we saw on the last slide wasn't dominant, but here we see an example of a dominant coloring, 1, 5, 6, and 2, 3, 4. I've split the colors up as equally as possible. And the significance of these dominant colorings is that they have the most entropy. If we want to maximize the number of pure AB colorings, of course, I should split the color set half and half. Okay, I'll call a coloring F an AB coloring if I color everything on the left A and color everything on the right B. And I'll say that a coloring agrees with this pattern AB if basically it follows this picture, right? So if V is on the left, V is in the odd sublattice and it's colored A, or if V appears on the right and it's colored B. And lastly, if I have a coloring, I can identify the pattern, the dominant pattern it agrees most with. And I'll call the other vertices, those vertices that disagree with F, the defect vertices of these colorings. So again, it's best just to look at a picture. Here we see we're sort of globally agreeing with this coloring A, comma B, but we have these sort of defect vertices that are going against the grain. Right, so are there any questions on those definitions? I've thrown quite a few terms at you. Maybe I'll just give you 10 seconds to absorb those definitions. Okay, great. And I'm kind of going to try and understand colorings by what the defects look like, because I expect, perhaps, I went in the back of your mind to think of a typical Q coloring to sort of globally agree with a pattern, but then there are going to be these sort of defect, deviant vertices doing different things. So really the challenge is to understand the distribution of these defects if we want to really understand what a typical coloring looks like. Okay, great. And a theorem of Engbers and Galvin already goes some way to understanding this question. So what they show is that if I let M be even and Q be some number of colors, and I let X be the proportion of defect vertices in a uniform coloring of my torus. So here I'm letting X be the fraction of the total number of vertices. Then the probability that X is bigger than e to the minus ON is exponentially small. So it's with exponentially high probability, I have an exponentially small number of defect vertices. So this is already saying something quite strong, right? With exponentially high probability, all but an exponentially small fraction of my vertices follow the pattern, or all but an exponentially small fraction of the vertices are defect vertices. Okay, but they make a conjecture that actually you should be able to replace this quantity on the right-hand side by something much stronger. Should be exponentially small in the number of vertices in the whole graph. So remember, n was the dimension of the torus. But the number of vertices of my whole graph is n to the n. And they make another conjecture, which is they give a conjecture for the number of Q colorings of the torus. So here I've given the conjecture for Q even to avoid flaws and ceiling symbols. Right, and so it's not too surprising that if I can really understand the typical structure of a Q coloring, I should be able to say something about the total entropy, the total number of Q colorings I have in the first place. And they make this conjecture. So we'll be able to, the theorem I stated earlier implies both of these conjectures. And in fact, we'll be able to say something much more. We can sort of get much stronger asymptotics here, in a sense, arbitrarily strong asymptotics on the number of Q colorings of the torus. So let me just give you a little bit more. Yeah.
So should I think of this as some extremal thing, right? So just to make sure I understand right, you're saying we're picking this optimal pattern for each realization or some, yeah, for each realization of the coloring, or yeah, right? And then, yeah, so should I think of this optimal pattern as some extremal, or rather this measure, some extremal measure, yeah, that happens to match really closely with.
Yeah, so you can think of like, right, you can think of these dominant patterns as the kind of, if you like, some extremal construction. And then again, and the intuition is that we have some stability around these extremal constructions. A typical element, and this is a common theme in combinatorics, if you have an extremal combinatorics problem, often you have these special examples, and almost all instances of the problem look like one of these extremal constructions, modulo some perturbation.
Got it. Thanks.
Okay, great. So let me just give a little bit of history on this coloring problem whilst we're here. So if I let CQG denote the number of Q colorings of my graph, Galvin showed that the number of 3 colorings of the hypercubes, so here I'm specializing to the discrete torus of side length 2, gave an extremal formula for the number of 3 colorings. Later, Kahn and Park gave this asymptotic formula for the number of 4 colorings. And here are just some fun formulae that fall out of our work. We can get asymptotic formulae for CQ for any Q, and here are some examples. These two confirm a conjecture of Kahn and Park. But what's interesting here is actually we can interpret each of these terms as understanding higher and higher cumulants of this perturbation distribution on the defect vertices, the distribution of defect vertices. And so in a sense, we can actually show that if you want to get an asymptotic formula for CQ, the number of Q colorings of QM, you really need to know all the cumulants up to roughly the qth cumulant. So you really need to, the number of terms is going to grow larger and larger, and you're going to need to understand the distribution of defects at higher and higher resolution if you want to get asymptotic formulae. And of course, we don't need just the hypercube, we get asymptotic formulae for the number of Q colorings of the torus, and more generally for any partition function on the torus. So for example, number of independent sets in the torus, generalizing a result of Korshunov and Safajenko, who determine the number of independent sets in the hypercube. Okay, so I said this comes down to understanding this distribution on the number of defect vertices. So let me say one of the things that follows from our main theorem. Let me now let X be the number of defect vertices in a random Q coloring of the torus. So again, we're just taking a uniform Q coloring of the torus, and I'm asking for how many deviating vertices are there. We might be interested in the number of them. How far are we away from one of these idealized extremal constructions? And we can prove a central limit theorem on this random variable. So we showed that if M is 2 or 4 and Q is 3 or 4, then the number of defect vertices is Poisson. And in all other cases, we get the central limit theorem. So I just want you to notice there's actually a sharp jump here in behavior. If we fix, for example, M equals 2 in the hypercube, then as we go from 3 and 4 colorings, for 3 and 4 colorings, we only expect a constant number of defect vertices. So 4 colorings of the hypercube are extremely rigid. They really are just an idealized A-B coloring, 2 colors on the left, 2 colors on the right, and then some constant number of deviations. And then for Q equals 5, we get a sharp change in behavior where we actually expect to see exponentially many deviant vertices. And this jump represents why it's more difficult to sort of enumerate 4 colorings of the hypercube, more difficult to enumerate 5 colorings than 4 colorings. Okay, so yeah, just the thing I want you to take away is that we can really actually quite closely understand the distribution of the number of these defect vertices. And like in the last slide, the way of proving these things is understanding higher and higher cumulants of these random variables, which I'll hopefully get time to say something about in a few slides' time.
Matthew, is this Fn also for odd Q, or did you write the even Q case?
Yeah, sorry, I wrote the even Q case. Yeah,
okay.
Ignoring a bunch of odd and even. Yeah, floor and ceiling symbols. Yeah, I should have mentioned that. Yeah, for odd Q, you get another formula. Great. Okay. So let me just give you an overview of the proof. Again, we're going to just let mu sub q denote the uniform measure on Q colorings. And as I hinted at earlier, our goal is to construct this new measure mu hat by randomly perturbing some dominant coloring. And we're going to try and show that mu hat is very close to mu q. And the gain is that we're going to really understand this random perturbation very well. So how are we going to get a handle on this perturbation? What we'll show is that these perturbations have the distribution of what's called a polymer model with convergent cluster expansion. Again, I haven't defined what these terms mean, but I will do soon. But in case any of you have heard of these terms, hopefully just give you some idea. If we can show that, if you can show a polymer model has convergent cluster expansion, you're really on your way to understanding this distribution very well. But proving this convergence actually is quite a difficult task, and that's what occupies the majority of our paper. And so to prove the convergence, we use a number of different tools, entropy methods, graph containers, the isoparametric inequalities in the torus, and some of the algebraic structure in the torus. But today I really want to focus on these statistical physics tools of polymer model and cluster expansion. And so let me mention actually that these methods first came to my attention in the algorithmic setting. So a paper of Helmuth, Perkins, and Rechts, they use these tools, these classical statistical mechanics tools, to devise efficient sampling algorithms for a number of spin models on the integer lattice. And there they use something more general than polymer models called contour models and tools from Pirogov-Sinai theory, which come with their own cluster expansion. And the treatment that we'll be talking about today follows a bit more closely some subsequent work of myself and Peter and Will on coming up with efficient sampling algorithms for the hardcore model on expander graphs. Okay, and following that work, the cluster expansion has also been applied to combinatorics. So recently, me and Will used these methods to say some things about the hardcore model on the hypercube, and then later Balog, Garcia, and Lee used it to enumerate the number of independent sets in the middle two layers of the hypercube. And let me also say that this combination of entropy methods and graph containers originated in the work of Pellet and Spinker, and then was later used in Kahn and Park. And so those two papers inspired a lot of this work as well. So entropy and graph containers of themselves have been used to study spin models and graphs in a number of different settings. But often, mostly they've been used quite separately, and this sort of marriage of these two methods is fairly new and recent, starting with this work of Pellet and Spinker. Okay, so that's an overview. So if there aren't any questions, I'll start talking about the proof a little bit. Great. Okay, so let's go back to our setting.
So you say that, so just background, so what is in, can you go back to the previous slide? So,
yeah.
So what did you say was in Kahn and Park?
Again, they also use this kind of combination of entropy methods and graph containers, sort of very much in conjunction.
For which model do they use it?
So this is in their paper for studying 4 colorings of the hypercube. I think their paper is called on 4 colorings of the Hamming cube.
Okay.
Matthew, I also have a question, a very imprecise one, but just to get maybe some idea. What would you say is more work, showing that the mu hat is close to mu, or understanding mu hat?
Yeah, that's a very good question. In some sense, they're equal amounts of work, but for the following boring reason: to do both, we need to show that these things have this. We have to show that this cluster expansion converges. So really, all of the work is showing that this polymer model, which is going to model our deviations, our defects, we're going to be showing that this converges. And that's going to help us to understand mu hat and to help us show that mu hat and mu are close.
So after you do the basic part, is the additional 2 steps of understanding mu hat and the relationship between mu hat and mu, is that more like general framework of a convergent of a cluster expansion polymer models, or is that model specific?
Let me think. So how do you mean? So do you mean the way we understand mu hat, does it fall within sort of the usual applications of the cluster expansion? Or?
I guess, yeah. I mean, I guess part of my question is, if someone wants to learn cluster expansions and polymer models,
yeah,
right? Just the idea of mu hat, mu, and so forth. Is that part of the idea similar everywhere, or is that also something?
So yeah, it's a little bit different here, and I'll be getting to it in a second. And the reason is, so if you wanted just to understand cluster expansion and polymer models, I would encourage you first just to think about the hardcore model, but at very high temperature, so very small fugacity, very sparse gas. And here, like, correlations are decaying exponentially, blah, 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 and you can really get like a handle on the cluster expansion in that case. And that's more the traditional use of polymer models and cluster expansion. What's a little bit different here is that here we have a low temperature model, so we have this large scale order, but we're looking at the defects and modeling that as a sparse gas. So I want you to be thinking of the defects themselves as behaving like a dilute or sparse gas. So we kind of flip the picture on its head a bit. So in that sense, it's a little bit different and maybe not the best way to first learn about these tools. Yeah.
Okay.
Great. So, okay. So yeah, let's get back to our problem. So again, we're looking at the torus, and we have this odd sublattice and the even sublattice. And I want you just to think of this extremal coloring. So we have half the colors on the left, half the colors on the right. And there's quite a few of these colorings already, right? We have q/2 choices for every vertex. So in general, we have q/2 to the m to the n AB colorings. M to the n again is just the number of vertices in our torus. And now I want you to imagine adding a little droplet of defect vertices. So a few vertices that are going against the grain. And I'll call this the set S. The set S is going against a global pattern. And I'll let the weight of S be the number of colorings that look like this, that disagree precisely on S, like in this picture above, compared just to the number of pure AB colorings. And if you think about it for a second, this ratio will always be less than 1. So this is going to be interpreted as like an entropy cost of deviating on S. The reason why it's less than 1 is as soon as you have an edge that looks like this, this has to have a color in B. Red probably wasn't the best choice of color here, but bear with me. And this also has a color in B. And so whereas before I had q/2 choices here, I now have fewer because I exclude a color in B. So I've got at most q/2 minus 1 choices. So as long as my deviations are relatively small, this comes with this associated cost. So this weight I want you to think of as an entropy cost of deviating at that set, and precisely that set. Okay, and with that definition in mind, I'm going to now show you a new way of sampling colorings, and this is how we're going to be thinking about Q colorings and understanding them. So here's a new model. First, I want you to select a dominant pattern uniformly at random. So maybe we land on this one here, 1, 2, 6, 3, 4, 5. Okay, and once we've selected that, I want you to select a set S with probability proportional to this weight, which we defined on the previous slide, this entropy cost. And then I just want you to uniformly pick a coloring that disagrees with AB precisely on S. Okay, so now we've picked a Q coloring of our torus. Although this isn't very interesting, actually, I've just defined for you a uniform coloring again. So I want to say this is mu hat, but really to be able to get a handle on this, what I'll do is instead I'll put some restriction on this set of deviating vertices in my step 2. So we have some trade-off here. So I'm going to be calling a set of a sparse set S with probability proportional to its weight. We'll soon discover what sparse means. But there's some trade-off here. In some sense, I would like to just let sparse mean something incredibly strict. Maybe sparse means just one vertex. And then I really understand what a uniform coloring looks like, because then it just looks like a dominant pattern, except it deviates at one vertex. Except then we have no choice of mu hat being close to mu. So we have to come up with a sufficiently useful and general definition of what sparse means, so that A, we can get a handle on the distribution, and B, we can show that it's very close to the original distribution. So that's how we're differing from the normal uniform measure. Okay, and in order to describe what I mean here formally, I'm going to have to introduce some language from polymer models. Well, let me first say that our theorem is that, again, that these two things are very extremely close, exponentially close in total variation distance. That's the idea. And more generally, we get the similar theorem. Just to remind you, this isn't just about Q colorings. We can do it for this more general class of measures. Okay, so once we have this theorem, it's really just about understanding mu hat. Okay, so a polymer is going to be a set of vertices in my torus, which I kind of want to just call it a connected set. Of course, that doesn't really make any sense if my set S is on one, is like in the odd sublattice. So what a polymer will be is a set of vertices such that between any two of the vertices, I can create a path where these all have distance at most 2. So if you like, in graph theory language, the square of the graph induced on these vertices is connected. So between any two vertices in my polymer, I can walk from one vertex to the other, and each step in my walk, the two vertices are at distance at most 2. So in other language, G squared of S is connected. Okay, let me get rid of that rather bad picture. I'll say a set S is small if it occupies a small 1% of my graph. And I'll say two polymers are compatible if their distance is greater than 3. So what's the point here of these weird definitions? So notice that a set S, any set S will decompose into some collection of compatible polymers. I just decompose G squared induced on S into its connected components. So just think of S as breaking up into these like connected pieces. And I'll call a set sparse if all of the polymers that comprise S are small. So that's what I mean by a sparse set in the previous slide. What's the point in making any of these definitions at all? Well, it's this nice property that if I have a set S and it decomposes into polymers gamma 1 up to gamma k, it breaks up into these polymers, then the weight is multiplicative over these polymers. So you can kind of think of these as like independent. These weights are independent of each other. So that's the main reason for making these definitions. Okay, and now I can just rephrase the distribution you had, but more formally. So again, what are we doing? We're selecting this dominant pattern AB uniformly at random. Then in step 2, I'm going to select a collection of small polymers, a collection of compatible small polymers with probability proportional to its weight. And remember the weight factorized like this. So now that's the formal definition of selecting these defect vertices. And again, I pick a color that disagrees on these polymers. And this type of distribution in step 2 has got a special name. It's called, unsurprisingly, a polymer model. And this very special structure of this distribution is what allows us to understand it so well. I'm going to be understanding it via the cluster expansion. So the partition function, which is just the normalizing constant that makes this a polymer model, is what I'll call the polymer model partition function. It's the sum over all collections of compatible polymers, the product of its weights. So this is the normalizing distribution of this step 2 here. So now I've just remodeled these defects as this funny polymer model. And now my goal is to just try and understand this polymer model. Because step 1 and step 3 are quite easy. They're not very mysterious. All the mystery is in step 2, like what's going on with these defects. And I've modeled them as this polymer model. And again, going back to Inan's question, what I was saying earlier is really the takeaway here, if you take away anything, is that these defects are behaving like a very sparse gas, or even more simply, these defects are sort of just popping up independently of each other. They're very uncorrelated. So even though the Q coloring itself is highly structured, is really globally following this pattern, the defects are incredibly unstructured. These defects are essentially independent of each other. And that's why we can understand this distribution so well. So this was the kind of flipping on its head that I was talking about earlier. Let's understand the defects rather than the global coloring itself. Okay, and a very powerful and typical paradigm in statistical physics is to understand these models. It's actually often enough to really understand just the partition function. So let me try and get a handle on this partition function. This already contains a lot of distributional information about my model already. Okay, and this is where the cluster expansion comes in. So the cluster expansion is a very powerful tool in classical statistical mechanics. But at first meeting, it's just a way of expanding the logarithm of the partition function. And actually, as de Bruijn observed, it's actually just the multivariate Taylor series of this guy. If I just consider each of these weights, that's their own complex variable. And actually looks quite similar to the partition function itself, except there's two key differences. So in the partition function, I'm summing over all compatible collections of polymers that kind of don't overlap. And here, I'm summing over a different kind of object called a cluster. And I'll explain what a cluster is in a second. And the other less crucial difference is that there's this real number here. This is the cell function of the cluster. I won't define that, but it's just some real number that you associate to the structure of this cluster. But the important thing is, what is a cluster? Let's understand that. So a cluster is just a multiset. Actually, it's an ordered multiset of polymers. Let's say gamma 1 up to gamma k. And what's the property? Between any gamma I and gamma j, I can find a path of other polymers in my cluster. And what's the property of this path is that the distance between these two polymers is less than 2. So if you like, it's like a polymer of polymers. Maybe it's best to draw a picture. So a set of compatible polymers look like this, maybe. We have some collection of graphs that are mutually very far away in the graph. But a cluster looks like this. You have some collection of polymers which themselves form like a connected graph when you look at their union. So it's like a polymer of polymers. So we're summing over two very different objects. Okay, but it's not too important to fully understand this formally. I just want you to understand sort of the general form of what the cluster expansion looks like. And hopefully in the last few minutes, I'll be able to show you why it's useful. So again, our goal here is to show that the cluster expansion converges. I should mention that this is an infinite sum. For example, these are all clusters. If I just repeat a polymer over and over, that's one boring example of a cluster, and we certainly have infinitely many. So unlike this sum up here, that's the other crucial difference. Unlike this sum is an infinite sum, and so the question of convergence is non-trivial, and we need to check that this series actually converges. And a lovely sufficient condition from convergence is given to us by a theorem of Kotechi and Price, which says that if for any polymer gamma, if I can show that as I look at this exponentially weighted sum over all other polymers incompatible with gamma, distance less than 2, if I can show this inequality, this just means the size of gamma, the number of vertices. This is a sufficient condition for the cluster expansion to converge. And actually, this is deeply connected to the Lovász local lemma. So if you haven't heard of Kotechi and Price, you actually have, because if you've heard of the Lovász local lemma, they are in some sense equivalent. Okay. So in the last few minutes, I'll try and just give you a sense of why this is useful, why understanding cluster expansion can be useful. And it goes back to something I mentioned earlier about understanding these cumulants. So let's go back to our polymer model. And let me try and understand the number of defect vertices. So let me let gamma be a random polymer configuration. Remember what that means. That was this collection of defects that I chose at step 2 in my mu hat distribution. And I might want to understand like how many defect vertices there are. So how many vertices of my graph in total are there here, these kind of deviant vertices. So I might want to understand the size of gamma, meaning just the sum of all the polymers it contains. Let's suppose I want to understand this random variable. Okay, so here's one way of understanding it. Consider a polymer model where you modify the weights slightly. So I'm going to update the weights. T is some positive number, say, and I'm just going to do this exponential tilting on my distribution. So now I'm going to, instead of the weight of gamma, I'm going to make the weight of gamma times e to the size of that polymer times t. So I'm exponentially tilting this distribution. And let zt denote the modified partition function. So what does that look like? Zt is just the sum over all compatible polymers times the product of their weights. That's the definition of this new partition function. And I want to compare this to z. Well, if you just write out the definition, what we get is that this is the sum over all compatible polymers, e to the t, the size of this whole collection, times the product of the old weights, just plugging in the definition. But if I rewrite this like this instead, notice that this is just the probability of seeing the collection gamma in my old model. And so here I'm getting the exponential generating function of the random variable I'm interested in. Okay, but it's a little bit tricky to understand this ratio. So instead I'll understand the logarithm of that ratio. And so instead of the exponential generating function, I get the cumulant generating function. And how am I going to understand the cumulant generating function? I'm going to apply the cluster expansion to this partition function. So what does that look like? So here I've just written that last line again to remind you. The cluster expansion is again just the sum over clusters times this real number phi of c, doesn't matter what that is, times the product of the weights of all the polymers in my cluster, these new weights. I'm just writing out the definition. I get this, e to the size of my cluster. So this is just an exponential tilting of my original cluster expansion. And so if I want to understand the cumulants of this, I just need to look at the coefficient. If I want to understand the kth cumulant of this random variable, I just need to understand the coefficient of t to the k in the Taylor series of the cumulant generating function. So the kth cumulant of the random variable I'm interested in is just the kth derivative with respect to t of this cluster expansion evaluated at t equals 0. But I'm happy because I showed that this cluster expansion converges absolutely. So I just differentiate within this infinite sum, and I get this expression for the kth cumulant. And now just the moral of the story is, if I understood the cluster expansion very well, I can understand all of the cumulants of this random variable very well. And I can start saying all sorts of things about its distribution. So this is precisely how we proved the central limit theorem I showed you at the beginning of the talk. Okay, great. I think that's all I want to say on cumulants. Just in the last few slides, let me just say a few words about how we show that the cluster expansion converges. So we're trying to verify this Katecki price condition, this Lovász local lemma type condition. And really this just comes down to two things. We want to sort of balance the weight of a polymer. So as polymers get larger, their weights become smaller and smaller, but that's fighting against the fact that the number of polymers that are large gets larger and larger. So these two things are fighting against each other. So we need to balance the weight of a polymer of a fixed size and the number of polymers of that size. And that's where this notion of graph containers comes in. Essentially, you just replace polymer by a notion of approximate polymer. Or maybe this, I think this is sometimes called a coarse graining technique in the probability literature. And the win here is that the number of approximate polymers is far fewer than the number of polymers themselves. So you get that entropy win there. And then we use entropy arguments to bound both the total weight of polymers with a fixed approximation and the number of them. That's where the entropy method comes in. And then we need to use some algebraic properties of the torus to reduce this entropy even further. It's not quite enough. And it's still not quite enough. Somehow we need to use these isoparametric inequalities in torus to tip the balance between 1 and 2 fighting against each other. So that's a very high level view of what's going on here, and that's really occupies the majority of our work, carrying out all of these steps. Okay, and then the last couple of minutes, let me just mention a few directions of future research. So it'd be really lovely to go back to the kind of classical statistical mechanics setting of the integer lattice. And the problem with just trying to blindly transfer what we did in the torus to the lattice is that the lattice doesn't expand very well. It's a terrible expander compared to the hypercube. So it's got much weaker isoparametric properties, and that's really kind of what the limit is for just blindly transferring these methods. But nonetheless, we have some ideas of how to do this, and the idea is to kind of, instead of doing polymer models, do what's known as contour models from Pirogov's-Sinai theory. It's just basically a more clever and nuanced way of defining defects. Instead of just saying this is where they disagree, you start to talk about boundaries between different dominant phases. And we think that for the polymer module intuition, even when you do this more nuanced technique, gives you the right intuition of what's going on in the integer lattice. So in our paper, we give some conjectures for what's the exponential growth rate of the number of Q colorings of a growing box in Zn or in the torus. Now it's the dimension is fixed, but the side length is growing. Or the exponential growth rate of the number of independent sets. I didn't define what I is. So this is the number of independent sets in the torus. What's the exponential growth rate of the number of independent sets of a growing box in the integer lattice? And we have some conjectures here, and we think the cluster expansion predictions should be correct. And I mentioned these more general framework. So Pellard and Inon, Ron and Inon, recently extended their work on Q colorings to a more general set of spin models, where now you allow soft constraints between particles. So I'm no longer restricting myself to considering just homomorphisms. And this more general class of spin models includes the easing model and the Potts model. So it'd be very nice to sort of explore to what extent our results enjoy generalizations to this setting as well. And lastly, just can we apply this cluster expansion method to other problems in combinatorics? So maybe not even on spin models on graphs, maybe not even graph problems, but in combinatorics, you often come across examples where this goes back to an earlier question, where you have an extremal construction, and a typical instance of some constraint satisfaction problem looks like an extremal construction subject to some perturbation. And can we understand these kind of more combinatorial problems using this cluster expansion framework, modeling the perturbations with the polymer model? Great, that's all I want to say for today. Thank you.
Okay, so let us unmute all to thank Matthew. I will stop the recording and we can have some questions now.
Great.